I think that I think that we are all getting used to these remote stints, and it works pretty well. Yeah, so what I'm going to talk about today is not so much NV centers, but some other topics that I've been working on, which is more related to many-body physics, and in particular this with spins. But before I enter into that, my group is the quantum engineering group, and so I want to give a little bit of a motivation of why we're interested in quantum engineering. So what do we mean by quantum engineering? As Adrisa said, I'm in the nuclear engineering department now, also in physics, and I'm really working at the interface between the two, where we are trying to use quantum mechanics to develop practical application and, if you want, the devices. So quantum engineering can be used to develop quantum computers, communication tool, sensing, we do a lot of that with NV centers, and quantum simulators. So what we want to do is really to take advantage of all the, if you want, quirky properties of quantum mechanics in order to achieve better performances for all of these type of devices. But to do that, we want to really have very large quantum systems and keep them coherent so that entanglement, coherence, etc., are of a size where advantages start to become evident. There's, of course, a challenge there, but we have the coherence and also information scrambling, which leads to a loss of an ability to look at coherent, locally accessible quantum information. And so we want to be able to sort of move from a small quantum system and go to a much larger quantum system, and trying to study how we can preserve their fundamental quantumness, if you want, and study what is somehow potentially preventing this. So what we have is that if you look at a few body quantum physics, we can really reveal, by now there's been tons of experiment and technology is always improving, so we can reveal coherent dynamics. The evolution is unitary, so if you want, reversible. But this happens when we look at single atoms, single MV, maybe small systems. When we start looking at very large quantum system, the language sort of transform into quantum statistical physics. So we start seeing the emergence of equilibrium postulates. We have to look at thermal ensemble. We want to use the language of phases of matter. And so what we want to do is to try to go from one place to the other, because really right now we are sort of entering the era where we do not really want to work on just a few qubits. We want to start working really on much larger quantum systems. And so we want to understand, as we grow our quantum system larger and larger, as we engineer devices which are bigger and bigger, what are the limits and how we can sort of overcome them. So some questions which have been arising and have become the topic of much more interest because technology is advances are: how does a closed quantum system, which in principle is completely isolated, and so it should evolve under unitary dynamics, which is a reversible dynamics. So how does such a closed quantum system end up thermalizing? And what does thermalization means for a closed system? And a question which is linked to that is what are the limits to the control of large interacting quantum systems? So how can we prevent this thermalization by, for example, using localization, using symmetries, using driving, and so on and so forth? So the first question, if you want, is a fundamental one, and the second one is a more practical one. So we go from physics to engineering of quantum systems. Because of the experiments that I do and my own interest, I'm sort of focusing not so much on general many-body quantum system, but many spin quantum systems. So the spin is the degree of freedom which I work typically with. And I've been using solid-state NMR, which is, if you want, a very old technology, and a technology which often is associated just with classical description of it. But we use this in order to get insight into this type of questions. So how can we say that we use NMR, nuclear magnetic resonance, and many spin system to try to answer some of these questions or to explore these questions? Well, if I just look at the dynamics of a spin system, so these ideas are already emerging. So let's say that I have, for example, an initially polarized chain of spins, and I perturb just one spin in the system. If I perturb it, it will start evolving in time. And if I look at local properties, this will look like some sort of decoherent behavior. So this is real experimental data in a solid state NMR system. And what I'm measuring here is the magnetization. Of course, it's the collective magnetization of my sample, but I look at single body properties. So magnetization of one spin average over the whole ensemble that I have in the system. And so because what I'm doing is to create a correlation among the spin, if I look at single body properties, I see a decay of my signal. Okay. However, this is the decay which happens because spins are interacting with each other. It's not a decay which happens because I have an interaction with noise. Of course, this is a real system, so at some point I also have noise relaxation, but this time scale for nuclear spin are very short. And so really what here it's dominated by the interaction among the spin themselves. So how can I be so sure? Well, what I can do is to say, instead of looking at single body properties, I can do a slightly more complicated NMR experiment, and I look at correlation among spin. And that reveals that really is not an information loss, but an information scrambling which is happening. So if I look at coherences, I see that here I have two spins which are correlated to each other on average. If I look at the later times, the number of spins which are correlated with each other is increasing, and I can recover a coherent signal. I will explain a bit later what exactly I'm plotting here. But here are just like the message is that I have signal even when, if I just look at this total magnetization, I had basically noise. If I look at my system in a different way, if I reveal the coherences, the signal is still strong at very long times, where apparently I would have just said, okay, my system has decayed down due to decoherence or something else. And so really these nuclear spin systems start to tell you, if you look at local observable, you see something which looks like thermal equilibrium. But if you're able to actually look at the correlation which are created in a system, you would see a coherent behavior. And so it's this is just using, if you want, traditional NMR techniques, so we can start to observe really in action these ideas which are centered around thermalization and scrambling of information. So we want to take this type of techniques and push them forward so that we can actually answer a bit more complex question which are, if you want, posing the language that we are using nowadays and sort of move a little bit away from the language that was, if you want, used by traditional NMR. So here is what I'm gonna more precisely talk about today. So first of all, I want to explain a little bit how we can observe the fact that we have this so-called heated discussion among your spins, which lead to a scrambling of the local information into the overall system. And I will introduce two metrics that we can use, the Loschmidt-Ekon and the auto-time order correlation in NMR. And I will focus in particular on the second one because it's been very much center of a lot of interest in the many-body community. And then what I want to do is to discuss three strategies. I will actually focus only on two, three only if we have time, but we can use to avoid this heated discussion. Heated because they lead to a thermalization, so an increase in temperature. So the first strategy is, of course, to avoid that the spins talk to each other. Even if they're hungry to each other, if they cannot talk to each other, we will not heat up. And so what we can do is to either look at integrable systems where we have no interaction, so the spin naturally, because of their natural interaction, will not interact with each other, Or we can, if we can, use control to decouple the spin to cancel out this interaction by using dynamical decoupling, but now for many body systems. The second strategy is to give to the spin something that they all almost agree on. So what that means is to create some sort of symmetries or conserved quantities so that we achieve at least a quasi-stable equilibrium, which is called prethermalization. And in particular, again, we will use control to do that, so it will be a Floquet prethermalization. The third strategy is to add some random gossip to the discussion so that in the end, spin are so distracted by this random gossip that they do not discuss with each other anymore. This can be done by introducing disorder, which can lead to many body localization. Again, this I will discuss only we have time very briefly. So first of all, how can we try to measure this information scrambling? I already showed a little bit how it can be done in NMR with these motivation slides, but here I want to give a bit more of a presentation about it. So when we have information scrambling, this is somehow connected to the classical idea of chaos, and so the butterfly effect. So if you have a small initial perturbation, this can cause very dramatic changes in classical systems, and they can be either sort of characterized by a Lyapunov exponent, and the dynamics is given by the Poisson bracket. For quantum systems, the same metrics that are typically used in classical systems are not as good because of the unitarity problem. If you have a slightly different initial state, this doesn't really give rise to this dramatic change. And we need to find some new metrics to study this scrambling. So what we can do is to look at something which is similar to this Lyapunov exponent, which is this, if you want, sensitivity of initial condition. And this can be somehow sort of extended to the so-called Loschmidt echo. So we cannot look at just differences in the initial state, which might give rise to different dynamics, so that doesn't really work out. But what we can look at is the evolution under some Hamiltonian of the initial state, and then a perturbed Hamiltonian. So this overlap with a small perturbation can indeed give rise to quite a difference and a decay of the fidelity between the initial state evolved under these two Hamiltonians. We can actually rewrite this for, in practice, state at infinite temperature as an overlap, a 2-point overlap between observable at time 0 and an observable at a later time, or if you want an observable evolved under either the normal Hamiltonian or the perturbed one. So this is the expression that we will be using actually in NMR to look at this type of sort of decaying and scrambling of the information. Another thing that we can do is to take the analogy between the Poisson bracket and commutator and look again at the commutator square. Looking just at a simple commutator will give a 0 result. So we look at the commutator square as a metric to try to figure out if indeed we have, if you want, a divergence of a path for our system. This second quantity is the so-called out-of-time order commutator, because indeed, if one expands the commutator itself, you start seeing, if you want, a 4-point correlator where the time order is sort of scrambled, is sort of like inverted. So how can we try to measure these autocs and why are they actually interesting to try to detect this scrambling? So this is another way of understanding it. Let's say that I have a local operator, again, for example, this spins which has been perturbed, and I have an operator which is sort of localized over a distant spin. And so at time equals 0, the two operators will just commute because they're basically localized so far away from each other that their commutator is 0. However, under evolution, what was an initial local operator might indeed start to have expand in the system. And at some point, it might have a support which is so broad, which also touches this far away other local observable. Then at this point, the commutator is no longer 0. And so we can sort of evaluate how much this force operator has been scrambled in the system by looking at the commutator itself. You see, it's good, but I'm not over there. Otherwise, everybody would be worried. He just when I speak too much. Okay. So even if it's sort of intuitive to see for commutator of local observable, how this will sort of give an idea of how much the system is scrambling, we can also look at extensive observable. I think I need much more water. Let's see. Okay, so we can look at the extensive observable, and they will give basically the same type of picture than local observable, because they're just sum of local observable. And this is something that we can have a handle in NMR, where everything is sort of collective. We don't have access to individual spins. So with these AUTOCs are then a good matrix of quantum information scrambling. And conversely, when information scrambling is not happening because we have localization or criticality, thermalization, we can also evaluate these type of things. So how do we measure them? So as a matter of fact, if you look at NMR, they've been measuring these since basically forever, at least for the past 40 years. So why were we interested in something similar? We were not calling them AUTOCs at all, of course. They were talking about a spin counting experiment in NMR. And the question was somehow similar to what we are trying to discuss here. If I create a correlation among the spins, this is like what we talk about when the information is scrambled, it's no longer local, I created a correlation. For NMR experimentalists, we were very much interested in knowing how many correlated spinning are out there, because that's related to the geometry and structure. If I have a coupling, maybe the spin will become correlated. If I don't have a coupling because the spin are far away or they don't have a chemical bond, then interaction doesn't happen. So NMR people developed these so-called spin counting experiment, which were really spectroscopic tools. And so they've indeed been measuring them for about 40 years. How do we do that? So we use a technique in NMR, which is called multiple quantum coherence. And we exploit two tools, which are proper of NMR, and you cannot really find in many other techniques. The first one is that we have an initial mixed state. And actually, it's a very, very highly mixed state, very high temperature. So of course, it's, sorry, forgot a minus here. We have a Boltzmann distribution as our state. And the main Hamiltonian is just the Zeeman interaction of the spin with the large magnetic field. So I can approximate this with just an identity matrix plus a small deviation, which is proportional to the total magnetization. The identity matrix doesn't really give rise to any signal, and so I can forget it. And my initial state is basically an observable, the magnetization itself. So in some sense, I can say, well, okay, I can do all my experiment as if I were at exactly infinite temperature. And then instead of having initial state with just identity, but I have an observable Z. The second tool that we have is that we can engineer time reversal using control. And so a typical experiment will go like this. I will evolve my system until some engineer Hamiltonian, and we'll discuss a lot about what we do to engineer the system. And this engineer Hamiltonian will create correlation among the spin. I'm then able to tag the correlation by doing rotations. And depending on how many spin are correlated, they will rotate with a phase which is n times the normal phase, and depending if I have n correlated spin. Then I use my ability to run time back, and so refocus the preparation step so that I can actually detect just the normal magnetization, because as in many other experiments, the correlation among spin do not really give rise to a signal in the experiment. So I need to sort of revert back to single spin observable. If I measure this signal for varying phase and take a Fourier transform, I will recover the so-called multiple quantum coherence intensities. These are basically how strong of a correlation, a Q quantum correlation I have in my state. It's so if you want, it's a partial tomography of my system based on how much correlation I have in the system itself. What was not really realized in NMR, except one single paper at some point, was that if I look at the second moment of my distribution of the intensity of the quantum coherences, this is actually equivalent to the out-of-time order commutator, evaluated again at infinite temperature with this trick where I used the density operator as an observable. And so we can use this to indeed extract this auto-commutator from the multiple quantum coherence distribution. And so how does the signal looks like? This is exactly this plot that I was showing before, talking about coherences. What we have here is that for each of the coherence order, negative or positive, again, this is just like if you want how many spin are correlated with each other in the Z basis, in the Z magnetization basis. And I plot the intensity of each one of them. The 0, 1 is always a bit too much because it's the one which does not decay due to any error. So we typically sort of ignore it a little bit. If I plot this distribution and I look at the width, this is going to be proportional to this out-of-time order correlator. And indeed, I can actually say that myself, I've been proudly measuring autox. I didn't know, but I was doing that already since my PhD back in 2006. This is one of the papers which we published then, looking at this MQC intensity. No reference to autox, no reference to thermalization or anything like that, but we were already interested in how correlation arises in a complex many spin system, because it's a useful tool to just look at the dynamics. The other experimental, this looks nice, but it's an experiment. I mean, this looks like simulation, but no, it's experimental data. This was from a more recent work with some Argentinian collaborator, Pastovsky in particular. So this is indeed one way of looking at scrambling of information. And now what I want to do is to look at how we can either avoid completely scrambling or how you can slow it down by using several methods. So the first strategy is indeed to try to separate the spin, if you want, put walls between them.
Can I ask a question?
Yeah.
So suppose that in this spin chain that you have, suppose that it's an integrable system, then you don't expect to have any chaotic behavior. Then how would this out-of-time order correlator look like for that case? I mean, you assumed from the beginning that there is a chaotic behavior, but we can start with quantum systems that are integrable.
Yeah, so I will show later on at least one plot, which hopefully will start answering that question. Basically, I expect that my autoc will stay constant and not evolve or maybe oscillate like along some small value. So if I look at, for example, non-interacting 1D chain, what I see is that I create, like in terms of multiple quantum coherences, I create only 0 and double quantum coherence. And so like if you wanted the width of my distribution is very tiny. And so autocs are small, and that's expected. They might not be completely 0 because, okay, I have correlation between 2 spins. Instead of just like having single spin magnetization, I have at least 2 spin correlated, but I don't have hundreds of spin correlated. And so indeed, autocs are going to be small. I will show another example in which what we do is to sort of use control to reduce the strength of the interaction. And indeed, we go from an autoc growing very fast to an autoc growing slower and slower. And if you were able to completely quiet down and have perfect dynamical decoupling, you would have flat, constant autocs at almost 0 value.
Okay, thank you.
So like the absence of growth of autoc is a good indicator that indeed you don't have chaoticity. I forgot that it becomes dark very soon and I didn't turn on the lights. Now you can see me. Okay. So dynamical decoupling. So what we want to do is really, if you want to engineer some spin choreography for many body systems. So probably many of you are indeed familiar with dynamical decoupling when you're considering single qubit, which is interacting with an environment, typically the phasing environment, and you do a spin echo or some more complex sequences of pi pulses to decouple from the environment. However, here we're interested in a slightly different problem. We have interaction, for example, the natural dipole-dipole interaction, which is among spin. And what we want to do is to cancel out these interactions. So we cannot just apply pi pulses. This will not cancel this. We want to engineer a more complex dance so that indeed the interaction goes to zero. It's very similar indeed to a ballerina, which if it's spinning fast enough, it's very much as if it were able to stand on one feet with perfect equilibrium. And people have done this for, again, in NMR for quite a long time. So this is a paper from 68, where they were already introducing a theory at that point on how to do coherent averaging of the coupling themselves. And we can build on this. We have a lot of history in NMR, but we can build to make this even better and understand better what are all the parameters that will make the coupling effective. So the idea is sort of the following: to apply some periodic pulses, for example, here 2 pulses that we can repeat many times. And this is, if you want, in the lab frame, it's actually the rotating frame of the RF, but let's consider this a lab frame. If I look at the dynamics in the frame, which is set by the pulses, what I will have is that in each time interval, I have 3 different Hamiltonians. So what I have is that the first time interval is just the same dipolar Hamiltonian. I haven't done any pulse yet. In the second time period, I've rotated my Hamiltonian to the X direction, and then in the third one, it's rotated to the Y direction. If I sum them up, as if I were able to do like a classical sum of the argument of my exponential of my evolution, well, will give rise to a 0 Hamiltonian, because Z plus X plus Y gives me exactly 3 times this sigma dot sigma. And so on average, we obtain that I have a 0 Hamiltonian, which is the desired result of dynamical decoupling. Of course, this is not perfect because I have higher order terms, in addition to, of course, also errors. And so what we are doing and what people have done in NMR and also what we are doing is to try to make this more and more perfect and also understand where does a problem arise from. So indeed, in NMR, there is a long history of starting from the solid echo, which is the sequence that I just described, and start to improve on them by using, for example, symmetrization, using cycle, and so on and so forth. So with a solid echo, you might know about a very famous sequence, which is Wahuha. MREV is symmetrization of Wahuha, which gives a better error. But then you start having more and more complex sequences. And indeed, I had to write a mathematical programs which plot out the sequences because it takes too long to write this. And for example, this sequence, Corey 48, by David Corey, there's 48 pulse sequences, so it goes outside of the slide. Okay, I can wrap it down, and so it's this long. So the sequence was generated in order to correct for various errors, make it robust, and so on and so forth. And like what people were doing was to basically use intuition, physical intuition, in order to figure out what are the errors, how they work out, and how we can correct them. But the question is, can we sort of do better than intuition only? Because the problem becomes very complex. We are trying indeed to optimize the engineering of the Hamiltonian where I have a many body system. And indeed, people have used optimal quantum control in order to somehow solve related questions. So for example, it was a very famous Grape Algorithm by Navin Kanajan back in 2004, which was one of the first, if you want, optimization done for quantum information, where by tailoring the amplitude of the control at each instant in time, here nanosecond times, you can achieve much higher fidelities. Of course, like if you invent something and you check NMR, you will always find that people have done it before. And so indeed, also just in the more classical NMR literature, not associated to quantum information, people had developed optimization tools, numerical optimization tools. In this case, what we were optimizing over was just a phase of a continuous drive. What is common to these two techniques is that they do a continuous optimization. So they have a continuous drive. Yes, it is discretized, but the discretization is very, very fine. So it is discretized because the experimental apparatus typically only allow you to do this, like digitization of your signal. So what you would like is to really have a continuous control, and you do a continuous optimization of your control sequences. And this is not really what works the best for many body. Also, it is quite cumbersome, and we sort of like move away from what we know works, which are these sequencing or discrete pi over 2 pulses. So we wanted to somehow not go down this route, but have some better optimization for if you want digital quantum control. So one of the first things that we did was to try to figure out if there were some rules to indeed improve, if you want, the digital quantum simulation. And here the idea was the following. Let's say that I want to engineer some target evolution, which is the sum of two Hamiltonians which do not commute with each other. And so I can try to approximate them by alternating evolving under A and B, because these are the only two Hamiltonian that I can actually engineer. I cannot engineer a sum of the two. So what you can think about is just to do a Trotter expansion. And so here, if you want geometrically, is what we want to do. We want to start from this point, initial state as initial state of the unitary operator, and we want to arrive to a final state of the unitary operator. In this case, it was 12A plus 8B, just as a reference, but we can only go onto this grid, where the grid represents evolving under A and horizontally, and evolving under B in a vertical direction. So of course, we can have many, many different paths. So I could take, for example, this path here, okay? Or I could take a path which has more switches. Which one is better? So of course, you can calculate what is the fidelity, but trying to optimize by calculating the fidelity is computationally inefficient. And so what we did was to find actually a geometric interpretation of the expected errors of this Trotterization of your dynamics. So the second order error is the area between the path and the diagonal, which represent, or if you want a straight line, which represent the path, the ideal path if you had a continuous or if you were able to directly sort of engineer the sum of the Hamiltonians. But we can also associate a geometric quantity to the third order error, which makes things even easier. So this is associated with the moment with respect to, again, the x-axis and this diagonal. And so we can calculate geometrically what is the expected error up to third order, which is typically good enough to have a very good approximation. And then we can use other dynamic programming to obtain the absolutely optimal path with respect to the third order. Or we can use a greedy algorithm to obtain a pretty good path, if you want, which is not optimal in terms of the third order error, but they already can achieve very good results. And indeed, this is the fidelity that we obtain. So here is plotted the log fidelity. So the second order trotter is this brownish path here, which has the lowest fidelity. And then the other two are this orange line, and the optimal one is the green one, which is expected the best for very short Trotter's types error, because it's the optimal in terms of up to third order. But when we start sort of having large enough Trotter step, this diagonal, which is obtained with a greedy algorithm, so very computationally efficient, start to become better. And so it's a very efficient way of calculating this optimal path. I've shown here for alternation between only 2 operators, but it's possible to also consider 3 or 4 or more operators if you have them available, and indeed calculate these optimal sort of trotterization schemes. In particular, this 2 diagonal is still efficient when you look at higher dimension. The 2 optimal start to become, of course, much less computationally efficient. So I think that like this 2 diagonal is a pretty good, if you want, optimization tool to have a better digital quantum simulation. Another thing that we did was, again, to say we want to do an optimization over a discrete set. And so typical gradient algorithms are not so good about that. So we use reinforcement learning in order to try to find, again, optimal sequences. And so what we did was indeed to sort of train a deep neural network. The action that the network can do are just like pulses. So we just decided that the operation that we can do are just pi over 2 pulses. These are indeed inspired by existing NMR techniques. And we test out whether the pulses are good or not on a spin chain. And we just calculated the fidelity as the metric for the action. Sorry, the reward for the action. What is interesting is that we actually find a novel pattern for the coupling. So if you remember the sequence, if you want all-time NMR sequences that I show you, they sort of like had always these 2 poles pattern, which were repeated maybe in different order with different colors, which correspond to the phases of the pulses themselves, but the pattern was always the same. Here we found the pattern which is different from that one. In particular, we found that the RL algorithm gives preference to having, if you want, an additional pulse, which was not found in the typical NMR sequences. There is, of course, a reason, because people in NMR were always trying to look at the, if you want, stroboscopic evolution. So they needed some window in between the pulses in order to be able to look at the dynamics. And so maybe somebody at some point thought about adding additional pulses and they discarded it because it was not practical. But this sequence is indeed something which was not in the NMR literature before. The simple sequence that we found was not as robust. And so what we did was indeed to bring back our human intuition, our knowledge of how symmetrization and errors work in order to now build some better sequences. In particular, because we found that this pattern was always fair, when we use them, we use the pattern itself as the building block, and no longer a single pi over 2 pulses, but we use this as the building block so that the space of searching for the algorithm is much smaller, we can find even better sequences. So by using these better sequences, this is the type of result that we find. These are experiments on fluorapatite, which is a particular spin system that we use routinely. If you just look at so-called FID, which is the free induction decay, you do pi over 2 poles, and then you do not do anything else. You let the system evolve. This decays down on very short time. This is the same, if you want, curve that I shown before with the multiple quantum coherences. If we apply what is the current best sequence from NMR, this Cori 48, this is the decay that you have. And if you apply our own symmetrized sequence, we have a much longer protection against the, if you want, the internal coupling between the system. So this is about 500 microseconds. So we go up to, if you want, 2 milliseconds, which is relatively long time. We still don't have effects from relaxation itself. This is much longer, on the order of, I think it's half a minute. So it is, sorry, half a second, which is much longer. But we still have effects of the coupling, which will be typically seen like this. So we are really able to slow down to, if you want, stop discussion among our spin for quite a long time using this. So this is like the fourth strategy, as I said, which is to try to stop spin from discussing. this is the second strategy that we want to do, is to give something to the spin that they can sort of agree on. For example, talking about the weather, something that everybody can agree. Today was nice. So before I go ahead, maybe I cannot see if people have a question. So maybe I'll stop briefly so that if you have a question, you can ask.
I have a question. Can you hear me?
Yeah.
Oh, sorry. Yeah. So depending on how you train your network, do you go to the same protocol, or there like a bunch of protocols?
Oh, like in terms of the coupling. So like the type of sequences that we were looking at were targeted at spin 1/2 coupled by so-called secular dipolar Hamiltonian. So the part of the dipolar Hamiltonian which commutes with, if you want, the Zeeman magnetization. But otherwise, that's about it. Okay, so indeed, there have been other sequences, for example, in the looking group, where we look at spin 1 in the presence of a very strong disorder, and there, if you want, the optimization would give a slightly different result. So I think that, like, yes, it does depend a little bit on the Hamiltonian that you're trying to indeed refocus. You could use the same technique, not only to do the coupling, but you could say, okay, I have a target Hamiltonian. I want to engineer a target Hamiltonian, and so I will try to do that. And so yes, the pattern will be different. In the experiments for this, so as I say, this was fluorapatite, which is a very anisotropic crystal, which is almost a collection, an ensemble of 1D spin. But we repeated experiments also in adamantane, which is much more a 3D system, and the results were similar. Like, you use different spectrometers, so like everything, like the errors that you have in the system are slightly different, but the results were quite similar. In the fluorapatite, we have some disorder. Is not super strong, but we have some disorder. And so indeed, we sort of like were trying also to make it robust against a disorder that not all sequences are. So Corey48 will also refocus disorder. So that's why we choose it to compare it to that. Like Wahoo will not refocus disorder, for example.
Thanks.
Okay. So as I was saying, like the techniques that we use were mainly like we apply them to do the coupling just because it's easier to find other sequences to compare to. And we wanted to make sure that, okay, we have good results with respect to what people have been doing. But in principle, you can extend them to also engineer any other arbitrary Hamiltonian. So beyond the coupling, what you can do is to do a so-called Floquet-Trotter Hamiltonian engineering, where you string along many different type of Hamiltonians in order to engineer on average a particular Hamiltonian. And the NMR, if you want a typical solution, is actually to apply these pulses in order to rotate the natural Hamiltonian and engineer this string of different Hamiltonians, as we saw for the coupling, but you can do it for other things. The question is, however, okay, if I want to use this to, for example, engineer some digital simulation or some like program my quantum emulator, will the fact that I'm constantly applying RF for NMR or lasers for other system, will that additional drive induce heating of the system? I turn on. I know that actually I have physical heating, if you want, and not in the spin degrees of freedom, but I'm applying some RF. If I'm not careful, things warm up for real. But even if you are thinking in terms of the spin degrees of freedom, are they heating up? Because I'm doing driving. And what has been a conjecture, also very much verified in numerics, is that no, this should not happen as long as your drive is fast enough with respect to the coupling, with respect to the internal energy of the system. And so what we wanted to do was to actually probe experimentally this answer here, which had been, for the moment, only looked mainly in numerics. And more precisely, if you want, what was a conjecture was that the dynamics of the system would sort of achieve a regime which is called prethermalization. So if you have fast enough driving, your system is sort of stabilized with respect to, if you want, a thermal equilibrium, which is given by an effective Hamiltonian given by your Floquet Hamiltonian, so like the Hamiltonian that you achieve by the periodic driving, and not, if you wanted, the natural Hamiltonian. So what you have is that maybe you start from, like for any given observable, you start from its initial value, it will decay fast toward its prethermal value, which is the value that it will have with respect to an Hamiltonian, a state which is thermalized with respect to this other Hamiltonian, but then it will stay on. It will not stay on really forever because you still have a little bit of heating, but the time that it stays stable is very, very long. So it's exponentially long when we consider the rate at which we are driving the system. So if you drive faster and faster, you can stay on for longer and longer. So how can we probe this? So one tool that we used, which was important, was to use Hamiltonian engineering in order to scale the dynamics instead of changing the rate. So why did we want to do that? Well, if I change here this tau, so the evolution that I have, I will also change how much, if you want the relaxation decoherence I introduced to the system, I might change how much control error I have. Instead, what we wanted to do was to keep the time constant so that decoherence, which is inevitable, is always there. But what I'm changing is the strength J of my interaction. And the strength H of the field in this case. So in this way, by using indeed tools from Hamiltonian engineering, I can keep what is not under my control fixed, and instead just changing in a controllable way the interaction itself. We looked in particular at a model that we can implement, which is the kicked dipolar Hamiltonian. This is, if you want, similar to the kick-Ising type of model. But here I had the dipolar Hamiltonian, which is an interacting Hamiltonian instead of the Ising one. So it's a bit more complex. And the dipolar Hamiltonian in this case is transverse. So the two Hamiltonians do not commute with each other. So how do we, what do I mean by that we use Hamiltonian engineering to scale interaction? So instead of just letting the system evolve under a natural Hamiltonian, we engineer the Hamiltonian by using this type of pulse sequences, which I discussed before. Now we do not want to engineer completely decoupling, we want to engineer a new Hamiltonian, in particular the dipolar along the y direction. And by changing the timing in between pulses, what I can change is indeed how strong J is. How can we actually measure that? So one way to measure that is by looking, for example, at the growth of auto-time order commutators. So if I look at this type of auto, it will grow under, for example, the XXZ interaction. So with the 1 over R cube coupling between spins, so typical spin-spin dipolar Hamiltonian. And this is what we observed. This was experiments actually done in adamantane, which is a 3D crystal, so quite strong coupling. So what we see is that as a function of time, the auto will grow quite rapidly. And we can actually relate that to how many spins are correlated. And so we see that we can sort of correlate on the order of more than 100 spins. So this is how large spins are interacting. But then I tweak what is my control. And as I said, I can slow down the interaction. So here, the Hamiltonian was slowed down by a factor of 1/2. So I have much weaker coupling between my spin. And correspondingly, what I observe is that indeed the auto growth become much slower. And I can slow it down even more and more. And ideally, if I were to put the scaling here equal 0, I would expect to have no growth at all. Now, of course, you always can achieve this slowdown and decoupling with some precision. So even for the scaling equals 0, we still had a little bit of evolution. But as you can see, it becomes much, much slower here. So yeah, so the autos are good at sort of diagnosing that you have a scrambling of your information, but they're also good at telling you, oh, well, if you do your control good enough, you do see that you don't have so much growth of the scrambling anymore. The correlation do not grow so much anymore. We did the experiments for the prethermalization in a different system, which is the fluorapatite. I don't want to say too much about this system. It's just that I really like it. It has an hexagonal cell structure where the spins are, the fluorine spins are much closer to each other in the vertical C direction than in the transverse direction. And so when you start putting more than one lattice cell on top of each other, what you start seeing emerging are chains of spins in this vertical direction, which are separated enough from each other so that the coupling in the chain are 40 times stronger than the coupling across the chain. And so what you have is that for some time scale, which is good enough for experiment, you really have 1D spins, an ensemble of 1D spins, which are relatively non-interacting with each other. And we also have some phosphorus spin around the fluorine, and we can use these to achieve disorder in the system. So we have been doing a lot of experiments in these systems instead of using like 3D system, just because it's much easier to sort of compare experiment to simulation, because the simulation in 1D system are much more manageable. For the prethermal, I don't expect that the 3D system will give me a fundamentally different result, but again, it was easier to have a sort of benchmarking. So going back to this Floquet prethermalization, what do we see? So as I said, what we wanted to see was that the decay of some conserved quantity, some prethermal conserved quantity was slowed down as we were sort of increasing the rate of the driving. And instead of really increasing the rate of the driving, what we were sort of changing was the strength of the interaction so that the drive becomes sort of faster in comparison. So here, what I plot is actually how the energy of the system varies, or if you want, the correlation of the energy of the system as it evolves in time with respect to the initial energy. And in particular, this is not the energy itself, but it's this prethermal Hamiltonian, which arises from these dynamics. So we expect, of course, that the prethermal Hamiltonian is a conserved quantity, so it becomes something which is sort of easy to look at in order to see if things are conserved or not. If I didn't have any heating at all, what I would expect is that all these cores, which are for different number of cycles, so like different times of my evolution, would just fall on top of each other. Instead, I have a slightly a small decay among them as time increases. However, like as you can see, the differences are not all that large. Okay, so again, if my driving is fast enough, I'm preserving my Hamiltonian pretty well. If the driving is not fast enough, then of course, I don't have this effect of prethermalization anymore. And we can explore a bit better this sort of like deviation of the cores from each other by looking indeed at what is the decay rate of this energy. Okay, and this is like this blue curve here. And indeed, we see that the decay rate sort of has this exponential behavior with respect to the driving rate. So the slower, the faster the driving rate, the smaller the decay rate itself. So if you want, it's logarithmically small in the driving rate. What was interesting was that we looked at the energy and we were thinking, well, the energy is something which is conserved and it should be the best conserved quantity. But actually, we found a different conserved quantity, which is, if you want, the first order deviation of the prethermal Hamiltonian itself. This is the dipolar Hamiltonian in the z direction. And this quantity, it's also a conserved quantity by the prethermal Hamiltonian itself, but it's even more robust. Its decay rate, so it has the same, if you want, a functional form, with exponential in 1 over the rate, but the coefficient is smaller. So it means that at some point, for a given driving rate, the Hamiltonian is no longer all that well conserved, the energy is no longer all that well conserved, but instead this other conserved quantity is. And this is something which is, I think, to us, it was quite surprising. It is still somehow surprising, but it's like from a practical point of view, it's quite interesting because it means that, well, you can study robust conserved quantity, quasi-conserved quantity using this Floquet prethermalization. And it's not just the Hamiltonian, so you have more things that you can explore and potentially exploit for applications. And also, it means that the energy is not the only thing and also not the most robust thing that you can preserve. And again, this I think should be somehow studied more in order to really understand when this is happening and what we can do with this. So I think that I don't know how I do in time. I think that I'm sort of over my time or almost. So I will just flash these results. So these are a bit older results, but this is basically the third way that you can try to stop thermalization, which is through localization. And we studied a little bit about this. We use, again, multiple quantum coherences to detect, or if you want autocs, to measure the average correlation length among spin. And we saw that this grows if you have ballistic evolution. It stops completely when you add disorder and you don't have interaction. You have Anderson localization, but you have a very slow, similar, it looks like a logarithmic growth where you have you're in the so-called MBL regime. How do I do in time? I can skip the application and just go to conclusion, or I can flash this.
I think it's what you want. Yeah, basically it's 5 now. So that's about time to stop, I think. But
so let me just go to the conclusions. So I think that what I wanted to convey today, especially talking a lot about NMR, is that the nuclear spin are really a good test bed to study many body dynamics and out of equilibrium dynamics, and a lot of questions related to information scrambling, thermalization, the lack thereof, prethermalization, et cetera, et cetera. And they're good because they have intrinsically very good coherence times. At the same time, they also have strong interaction. The systems are very large. We are really in the thermodynamic limit. And we have a long, long history of having good control. And we can also still come up with ideas to improve the control even more. Tools that we have been developing are tools in Hamiltonian engineering, also optimizing it using reinforcement learning, using our own intuition, and so on and so forth. And a lot of metrics that we can look at, including out-of-time order correlation, ACOs, and so on and so forth. So what we did was to explore various like interesting, I think, question related to localization and prethermalization. And this could be hopefully applied to simulation, to achieve quantum memory if you do dynamical decoupling, and also potentially to sensing either by doing decoupling or by creating interesting Hamiltonian. I want to thank the people that have been working on this. Initially, it was Ken, who's now has been for some time at IBM already. Pai has been working more recently on this. Yishang did the work on the optimized trautherization scheme. We have a long-time collaborator in Shekhar Ramanathan, who's at Dartmouth. He's been working with us on the NMR experiments for a long time. And we also have a more recent picture. This is after COVID, taken outside, of course. And Andrew is going to inherit the setup and the ideas from Pai, who's going to graduate soon. And hire Pai if you want, because it's super good. This is Pai. I'll leave up my conclusion and take any question that you might have.
So yeah, let me quickly ask in the room here if people have any questions. And well, if not, then people on Zoom can also ask questions, obviously. But let me maybe start off with asking one question. Is that one of the things you said got me thinking a little bit. And this experiment about measuring the heating in this 1D almost decoupled chains is very nice. And then you said that you don't expect any large changes if you go to 3D, but one of the things I was wondering is that obviously I can prove this exponential slow heating if I have local Hamiltonians, but if I have 1 over r cubed in 3D, that would actually complicate at least proving it. So you think that it might be slightly faster because it's on the cusp of being long range?
Yeah, so well, yeah, so like it's on the cusp of being long range, so I don't know like if it's gonna be all that different. Even the 1D system, it is a 3D system, really.
I know, yeah.
So that's why it is like.
Well, I can rephrase it. Is it interesting to try to theoretically work it out so you can check it?
Well, I mean, I think that, I mean, so if you guys think that it's interesting for me to repeat the experiment on the 3D system, we can do that.
Okay.
Maybe it's easier.
Yeah.
To me, it was like, well, I mean, we are like the time scale that we are doing, we're already pushing where we know that coupling between the chain has started to be seen. Like we haven't done really anything to exploit the 1D-ness of the system in the control or anything.
Right.
So it's, yeah,
Okay.
but yes, I mean, if indeed 3D would be even more interesting, like it's like means recalibrating, like, okay, if my magnet can survive the next few days because we don't have any liquid helium and it's evaporating very fast. So I don't know if I'm gonna be able to do ever more experiments, but if it survives until Tuesday, then I will do the 3D.
Oh, nice. I don't think I can do the calculation by Tuesday.
No, I mean, I cannot do the experiment by Tuesday, but if the magnet survive until Tuesday, then after that I will be able to do experiments.
Okay.
It's
There's
like
a better question, I think.
Yep.
So you showed the graphs of the out of time order correlator as a function of the time, and I guess that you can extract from them the Lyapunov exponent. And I wonder how is it related? So recently there was some bound on the Lyapunov exponent that came from black hole physics, from holographic models. So I wonder how does the values that you get for this Lyapunov exponents, how do they relate to this bound?
I do not know. Like, because we are looking at these like collective autocs, so I think that extracting directly the Lyapunov exponent for the collective autocs, I'm not sure if there is really a relationship exactly. Like they give like qualitatively the same picture, but there are some contribution from the fact that you have indeed these collective observables, which are not in the typical like local autocs, which is more easily related to the Lyapunov exponent. I will have to check, but that's a very interesting question, and so I should indeed look at it.
Are there some questions on Zoom? Let me check. Doesn't look like there's questions on Zoom. So if not, maybe we can thank Paola again for the nice presentation.
Thank you.
Thanks for coming, or well, thanks for giving the talk, I guess. Well, if all works out, I will be in Boston in 5 hours if I catch my train. So
Okay, cool.
oh,
Sounds
thanks
good.
everyone.
For seeing you in person. Thank you
Yeah,
again
thank
for
you,
the
Paola.
invitation. Bye.
Bye.